In the summer of 2018, a convoy of tugboats dragged a 600-meter plastic pipe into the middle of the Pacific Ocean and dropped it into a field of floating garbage the size of 3 Frances. The pipe was supposed to bend into a giant U shape, drift with the currents, and somehow scoop up trillions of pieces of trash that had been piling up out there for half a century. It cost millions of dollars. It was designed by a kid who had dropped out of college, and within 4 months, it snapped in half. The whole thing looked exactly like what the critics said it was, a fairy tale. Marine engineers called it a fool's errand. Government agencies had already run the numbers and concluded that cleaning the Pacific garbage patch with ships and nets would take thousands of years and cost more money than most countries have. Then established ocean scientists publicly said the idea ignored basic physics. One prominent researcher flat out told the founder to go back to school. And if you'd been standing on the deck of one of those tugboats watching a broken pipe bobbing uselessly in gray swells surrounded by an endless horizon of dirty water, you would have agreed with every single one of them. But here's the thing about that broken pipe. 7 years later, the organization behind it hit a milestone that no government, no Navy, and no international treaty has ever come close to matching. 50 million kilograms of plastic pulled out of the ocean and the rivers that feed it. Not promised, not projected. Verified, weighed, and hauled to shore. How a floating fence conquered the largest garbage dump on Earth. To understand why that broken pipe mattered, you need to understand what it was fighting, and the Great Pacific Garbage Patch is not what most people think it is. Forget the image of a solid island of trash you could walk across. That doesn't exist. What does exist is worse. Picture a stretch of open ocean between Hawaii and California, roughly 1.6 million square kilometers of water, and every single cubic meter of it is contaminated. It's a soup. Bottles, fishing nets, crates, lids, fragments, fibers, chunks of foam, shards of hard plastic worn smooth by salt and sun, all of it suspended in the top few meters of the water column, swirling in a slow clockwise rotation driven by the currents of the North Pacific. From the surface, a lot of it is invisible. From a plane, it looks like the ocean has a rash. An estimated 1.8 trillion individual pieces of plastic are trapped in this vortex. If you started counting them one per second, you'd be counting for 57,000 years. And the deadliest material isn't the bottles or the foam. It's the ghost nets, fishing gear that was lost or dumped by commercial fleets, nets designed to catch things, and they never stop. They drift through the gyre, tangling sea turtles, strangling seals, wrapping around whales. Ghost nets alone account for nearly half the total weight of the patch. But the part that keeps oceanographers up at night isn't the big stuff. It's what the big stuff becomes. Every single day, ultraviolet light and wave action grind those bottles and nets into smaller and smaller fragments. Microplastics. Pieces so tiny they get eaten by the organisms at the base of the food chain, the same organisms that pull roughly 30% of our carbon dioxide out of the atmosphere and sink it to the ocean floor. Microplastics are jamming that process. The garbage patch isn't just ugly. It's a machine that manufactures poison, disrupts the climate, and gets worse every year that nobody touches it. And for decades, nobody touched it. Not because they didn't care, but because the math was brutal. A 2012 government estimate concluded that 67 ships running full-time for an entire year could cover barely 1% of the patch, at a cost of hundreds of millions of dollars. At that rate, a full cleanup would take centuries and cost more than the GDP of most nations. The ocean had won. The trash was staying. That was the consensus when an 18-year-old Dutch kid stood up at a TEDx conference and asked a question that sounded almost stupid in its simplicity. Why move through the ocean, Boyan Slat asked, if the ocean can move through you? The idea was this. Instead of sending ships to chase plastic across 1.6 million square kilometers of open water, you build something that acts like a coastline. A long, floating barrier shaped like a U. You put it in the path of the currents, and the currents push the plastic into it, the same way waves push driftwood onto a beach. You don't power it. You don't chase anything. You let the ocean do the work. Think of it like a dustpan. You don't chase dust around a floor. You sweep it into a corner where it piles up. The ocean current is the broom. The U-shaped barrier is the dustpan. And the trick is making sure the dustpan is always in front of the broom, always moving just a little bit slower, than the debris coming toward it. That tiny speed difference, about 1.5 knots, roughly half the pace of a person walking, creates a funneling pressure inside the U shape. Plastic slides along the inner wall, concentrates at the bottom of the curve, and gets held there by the same current that pushed it in. It can't drift back out because the barrier is always maintaining that funnel effect. The concept was elegant, but the engineering was a nightmare. Slat dropped out of Delft University, founded a nonprofit called the Ocean Cleanup with 300 euros in his pocket, and started raising money through crowdfunding. He pulled in $90,000, then $2 million, and then eventually over $30 million from Silicon Valley investors and global shipping companies. By 2018, he had a team of over 150 people and a prototype ready to test. That prototype was System 001, nicknamed Wilson, a 600-meter floating pipe designed to drift in the gyre and let debris accumulate inside its curve. It failed. And the reason it failed is the key to understanding why the system that replaced it works. The problem was speed. Both the barrier and the plastic were floating on the same surface current, drifting at roughly the same rate. When the wind pushed the pipe faster than the debris, plastic collected inside the U. But the moment the wind shifted and the pipe slowed down, all that plastic drifted right back out. There was no consistent force holding the trash in place. On top of that, an ocean swells fatigued the pipe material until an 18-meter section cracked and broke free. The critics had a field day. The project was publicly mocked. One prominent ocean advocate called it a dream that seduced many people. It looked like the whole thing was over, but here's what the critics missed. The failure taught the team the exact physics of why passive collection doesn't work in open ocean, and that lesson pointed directly at the fix. System 001 failed because it drifted at the same speed as the trash. System 002, nicknamed Jenny, fixed that by towing the barrier slowly behind two support vessels. 800 meters of barrier crawling through the garbage patch, and the plastic piled up exactly the way the models predicted. 28,000 kilograms in a single test. The screen hanging beneath the barrier extends 4 meters below the surface, deep enough to catch not just surface bottles, but the heavy ghost nets responsible for almost half the patch's total weight. Cameras monitor the collection zone in real time, and if a turtle or seal enters the area, operators open an escape hatch. The rate of accidental animal capture, less than 0.7%. By 2023, the system had scaled to System 03, a 2.2-kilometer-long barrier, nearly 3 times Jenny's length, with 5 times the collection capacity. The team doesn't sweep blindly. They tag debris with GPS trackers, feed ocean current data into computer models, and steer the barrier through the densest clusters like a combine harvester following the thickest rows of wheat. At peak efficiency, it sweeps an area the size of a football field every 5 seconds. And the team didn't stop at the open ocean. A study published in 2021 identified that just 1,000 rivers, barely 1% of the world's waterways, dump roughly 80% of all the plastic that reaches the sea. So while the barrier hunts legacy trash in the Pacific, a fleet of river machines called interceptors blocks the supply line. These are solar-powered autonomous barges anchored in the worst polluting rivers in Indonesia, Malaysia, Jamaica, Guatemala, and beyond. In Guatemala's Rio Las Vacas, a river so choked with waste it resembles a moving landfill. A heavy-duty version called the Interceptor Barricade was anchored into 144 cubic meters of poured concrete and built with technology originally designed to stop rockfalls and avalanches. In a single rain event, it captured 1.4 million kilograms of trash before it could reach the Caribbean. For the first few years, it didn't look like much. System 001 broke. System 001/B was a small-scale test rig, proof of concept at best. Jenny pulled in a few tens of thousands of kilograms and then went back for refitting. The critics stayed loud. The garbage patch stayed enormous. If you'd checked in on this project in 2020, you'd have seen a nonprofit burning through cash with nothing to show for it but a broken pipe and a theory about speed. The turn came quietly. System 002 hauled its first full load, 28,000 kilograms in a single extraction, and the collection rate in targeted hotspots ran 60% higher than in blind sweeps. The speed difference held. The retention zone held. The targeting worked. When it wasn't champagne and cameras, it was an engineer watching the tonnage numbers climb and realizing the math finally closed. Then System 03 hit the water and everything accelerated. The 2.2-kilometer barrier didn't just collect more plastic, it changed the economics of the whole operation. The cost per kilogram dropped to a point where industrial scale cleanup was feasible, not just technically possible. The barrier wasn't an experiment anymore. It was a harvester, and something unexpected started happening in the rivers. In Malaysia's Klang River, where interceptors had been running since 2019, the annual volume of collected waste dropped 82% by 2024, not because the machines were catching less, but because there was less to catch. Upstream waste management, sparked by the visible success of the interceptors, started improving. The river, once rated as severely polluted, improved to moderate, and then the animals came back. Otters, crocodiles, migratory birds, nesting eagles, species that hadn't been seen in those waters in years. In Kingston, Jamaica, 9 interceptors formed a citywide shield across the gully systems that drain into the harbor. The plastic that had been smothering coastal mangrove roots was physically removed, and the mangroves started growing back on their own. 6,000 square meters of habitat reclaimed without a single tree being planted. Engineers cleared the way, the ecosystem did the rest. Stand at the edge of the Rio Las Vacas during a rainstorm, and you'll see 2 worlds divided by a line of steel cable and floating boom. Upstream, a wall of plastic and organic waste moves like a slow glacier, 50 meters wide, deep enough to bury a car. Downstream, the water runs. It's not pristine. It's not crystal clear, but it moves. It flows. Fish break the surface. The riverbanks hold their shape instead of being scoured clean by trash-laden floods. That line exists now in over a dozen rivers across 3 continents, and out in the Pacific, the numbers tell the story that the naked eye can't see from the surface. As of early 2026, the combined ocean and river operations have removed 50 million kilograms of plastic from the world's waterways. Some of those recovered objects carry manufacturer stamps from the 1970s, crates and floats that circulated in the gyre for half a century, grinding into smaller and smaller pieces with every passing year. Every one of them has now been stopped. Each kilogram of large plastic removed from the surface today is a kilogram that will never shatter into microplastics, never choke the plankton that pull carbon dioxide out of our atmosphere. That interference is already costing the ocean somewhere between 15 and 30 million metric tons of carbon absorption every single year. The peer-reviewed environmental assessment published in 2025 calculated that 10 years of active cleanup would generate somewhere between 0.4 and 2.9 million metric tons of carbon emissions from the support vessels. Set that against the carbon absorption it protects, and the cleanup pays for its own climate cost many times over. Not in theory, but in published calculation. The economic model has shifted too. In Tangerang, Indonesia, when the deployment of a single river interceptor created 30 full-time jobs and scaled a local waste sorting facility from processing 200 kilograms per month to 600,000 kilograms per month. The recovered plastic from the Pacific is being processed into durable goods. A car manufacturer uses ocean plastic in interior components. A band pressed vinyl records from river waste. These aren't token gestures. They're the first threads of an industrial loop that turns a liability into a material supply chain. The full cost estimate for eliminating the Great Pacific Garbage Patch, $7.5 billion over 10 years, or $4 billion over 5 years, with an optimized fleet of System 03 units. For context, the world spends $2.5 trillion every year on the ecosystem damage caused by plastic pollution. The cleanup price tag is a rounding error. In 2012, the official consensus was that cleaning the garbage patch was impossible. In 2018, the prototype broke in half, and the critics said they told you so. In 2026, 50 million kilograms are out of the water, the technology is proven, the cost is known, and the fleet is scaling. Sometimes the most advanced engineering doesn't look advanced at all. It looks like a plastic pipe floating in the middle of nowhere, moving at half walking speed, letting the ocean push garbage into a bucket. No chemical treatment, no nuclear-powered fleet, no billion-dollar satellite network. Just geometry, fluid dynamics, and the patience to fail 4 times before getting it right. The ocean isn't broken beyond repair, it's a system trapped in a bad loop, and the loop has a mechanical fix. The same currents that concentrated the plastic into a patch are now being used to concentrate it into a collection bin. The same rivers that carried waste to the sea are now being fitted with barriers that catch it before it arrives. The garbage patch is not permanent, it's a finite engineering problem with a known solution and a price tag. The only variable left is whether we write the check. If that kind of story interests you, subscribe. There's more coming.